It was a very specific example.
On that note, let's begin recording. As we talked about yesterday, the figures in this chapter, the three-dimensional figures that we will be finding area and volume of are prisms, cylinders, pyramids, cones, and spheres. Today we're starting with the surface area of prisms and cylinders. And you'll find that there's a very nice, neat relationship between the prisms and cylinders, which is why we teach them together. And there's a nice, neat relationship between the pyramids and cones, and that's why we teach them together. So I was asking you before to sketch the net for problem 1 in order to get us ready for finding the area of this figure using the net. Not the way you're going to find the surface area from now on. From now on, what you'll see me do on the screen after this problem will be using the formula that we're using this problem to derive. So a little bit of vocabulary that you'll notice on the screen. We will talk about prisms, and when we name these prisms, we're naming them based on what kind of shape their bases are. Because we won't always have nice, pretty rectangular prisms. If you look at the bottom of your notes, you'll notice there's a hexagonal prism that we'll be finding the surface area of, among other things. So sometimes students struggle with identifying what the bases are in a prism. Let's make sure that we're clear on the vocabulary. Notice in your notes that the bases are the congruent and parallel bases. So if you're looking at a prism and there's a bunch of rectangles and then there's two other shapes, those other shapes that are congruent and parallel, I like to think of them as the odd men out. They are the bases. Whereas all of your lateral faces will always be rectangles. Okay, so in problem 1, we're going to find the surface area of this prism by, as hopefully you've already done, kind of mentally cutting it open, laying it flat, and finding the area of all of its faces and adding it together. Now the way that I'm going to draw this net is in a way to kind of naturally lead into why the formula does what it does. So bear with me if your net doesn't look exactly like mine. The way that I'm going to draw my net is by cutting it up along the height of the prism and then unraveling its lateral faces. So here's what I mean by that. There's the front of it. It's 10 by 5. Here's the right face of it. It is badly drawn, but you get the idea. It is 4 by 5. There's the back. It is also 5 by 10. And here's the left face of it, also measuring 4 by 5. Okay, so I've unraveled the lateral faces, and I'm just going to flip open the top above it and the bottom below it. So let me throw that up here and here. Once again, on your notes, if you sketch the net differently, you're probably just fine. The main things that you want to be mindful of is remember that the number of faces in the polyhedron is always the same as the number of faces in the net. Okay, so if you're looking at 5 rectangles, that's incorrect because we have 6. So just make sure that you have all 6 faces represented. All right, so the top and the bottom, once again, will be 10 by 4. So this one is also 10 by 4. And as I mentioned before, the way that we're doing this problem is kind of long and drawn out in the sense that we're opening everything up, finding the area of all of the pieces, and then we're going to add it together. Well, all of the pieces add up nice and neat because they're all rectangles, and the area of a rectangle is always just base times height. So this is 50 and 20, another 50 here, another 20 here. This is 40 and another 40. And when I add them all together, I have 100, 220 centimeters. And before I write it down, What do you think it is?
Square.
Is it square centimeters? Is it cubic centimeters? What do you think? No, it's not the number 4. Your sound split. And it's a common misconception that because this is a 3-dimensional figure, it would be cubed. Cubed is a volume measurement. That's what we'll be doing after break. What we've done here is found the area of a 2-dimensional figure. Notice, it was 3 dimensions, but we flattened it out. Now it's 2 dimensions. We found the area 2-dimensionally. Okay, so your answer is going to be in square units. Be very mindful of that.
So if you found it without making it,
It would still be area, and the area is still a square unit measure. Okay. So I made a big deal about how I drew it in a particular way so that it would kind of naturally lead into how we're going to come up with this formula. So what I want you to observe is you have it in the notes in front of you. I want to refer to it as I'm still looking at this diagram on my screen. Okay, so kind of bear with me with that. So it's asking you in your notes to notice that the part of the net drawn consists of the lateral faces. I'm talking about this part of my net. This is where I took my 3-dimensional figure and I cut it open and I said I was unraveling the lateral faces. Well, look at that black, oh, I almost gave it away. What kind of shape is that? It's not a square, it's a rectangle.
is it a rhombus?
It's definitely not a rhombus. Okay, it's a rectangle. And we know how to find the area of a rectangle. The rectangle is base times height. So think about it. Look at this black rectangle that I've highlighted on the screen. Look at where it came from in the original figure. The base of that black rectangle is what as far as the original polygon is concerned? Let me ask you a different way. Look at what the base of this black rectangle is. It's 10 plus 4 plus 10 plus 4. Look, I'm not interested in what the number is as much as I am interested in what is it in the context of my original figure. Sir? It's the what of the top. That's not the area of the base. It's 10 plus 4 plus 10 plus 4. What does that sound like? It's the perimeter of the base. Yes. So let's make sure that we're filling in these blanks together here. Okay, so that unraveled lateral faces part of our net is in the shape of a rectangle. The base of the shape is the perimeter of the prism's base, while the height of the prism is the height of the rectangle is the height of the prism. So if I was asking you for the lateral area of the prism, what I would in essence be asking you for the area of would be that black rectangle that I had in the previous screen. Sir?
You know, it's the long black rectangle.
Mm-hmm.
You knew it was that because it had 2 bases, right? And not say it's vertical.
If I had a rectangular box.
I have a rectangular box.
Here. Oh, here. I want to cut it open.
You want to cut it open?
No, I don't want
Oh.
So, let's visualize this as that prism that you saw on the screen. If I were to cut it open here, if I had scissors. Here we go. If I cut it open here, this is not going to work. But do you visualize that this green part of it would unravel and be a very long rectangle, like that black one we had on the screen. And that this length of that long rectangle, well, what is it? Look at the base. It's the perimeter of the base. Don't disagree with me to shut me up. Are we good?
Yeah.
Okay. All right, so the lateral area of the prism is, as I was saying, the area of that black rectangle, which is the perimeter of the base times height. And then surface area, well, what haven't I yet included in my calculations? What haven't I yet included in my calculations? Let's look at that black rectangle. So far, all I've found is the area of that black rectangle. There's something else. The two bases, right. And what do I know about the two bases? They're congruent. Okay? So, our surface area is that P times H of the lateral area plus 2 times the area of the base. And I'm trying to make a big deal about giving you the formulas, once again, in the same way that you will see them on the EOC reference sheet. So let me just hand you a reference sheet so that you're looking at it and knowing what's where. But please don't take them with you. New reference sheet.
It's your normal
It's very.
It's not as orange.
Okay, so notice, gentlemen, notice that on the reference sheet where we have all these three-dimensional figures, on your reference sheet there is a key that clarifies what that P represents. The P is the perimeter of the base. Clarifies what that big B is. It's the area of the base. Notice the difference between the B's. That's a capital B. That's area of the base. Whereas last chapter we were dealing with lowercase b's being the base of a two-dimensional figure. So for the purposes of your notes, you might want to add that key here. The fact that P represents the perimeter of the base and that capital B represents the area of the base. And now that we have a formula, that's what we'll be using to find the surface area of prisms here on out. Is this thing in the way again? And we have from the screen what we need. You good over there? So you'll notice that number 2, the problem that looks like a your turn is the problem that we're actually doing together, whereas the one that looks like a problem is actually going to be our your turn. Okay, so in the number 2 that we see on the screen, we're going step by step in the process of finding the total surface area of this hexagonal prism. First step is we're finding the lateral area of the prism. One thing I wanted to make sure to mention, look again at the reference sheet. Notice that nowhere on the reference sheet does it give you the distinction between the lateral area and the surface area. You are expected to realize, if you look at the formula on the reference sheet, there's the PB, PH, and then plus 2B. You want to make sure that you remember that the chunk before the plus sign, and this is true for all of the formulas in today's and Monday's lesson dealing with surface area. The first chunk, the stuff before the plus sign, is all lateral area. Okay? So in problem 2, part A, where I'm asked for the lateral area, times h. Okay, remember the P is the perimeter of the base, so that's 6 times 6, which is 36, times the height of the prism, which is 12. What kind of figure is the base of my prism? Okay, let's backtrack on the vocabulary. Remember that the bases are the two congruent parallel faces. You see that the two congruent parallel faces are the two hexagons. So my bases are hexagons. That's what I'm finding the perimeter of. That's what I'm finding the area of when I'm plugging in. It sounds like I've answered your question. Okay. So 36 times 12 is 432. And then in part B, I'm finding the area of the base. Remember, we talked about it just a couple of seconds ago. The base in this figure is a regular hexagon. Remember that its formula is 1/2 perimeter times the apothem. We already know what the perimeter of this hexagon is. It's 36. What's the apothem? What is the apothem? It's not 6. It's not 3. Let's visualize it. Here it is. 30, 60, 90. There we go. It's 3 radical 3. Remember, in a hexagon, the apothem is always half the side times radical 3. Always in a hexagon. Okay, so in part B, they're asking us for the area of the base in simplest radical form. So that's 18 times 3 with the radical 3 attached. And then finally, they're asking for the surface area of the entire thing. That's, remember, surface area equals pH plus 2 capital B. Well, remember, we already found what pH was. It's here. So that's 432. Plus 2 times, again, remember, we found the area of the base. We found it here. And now you're just typing all of that fun stuff into your calculator, since the instructions for part C said go ahead and round your answers to the nearest whole number. Giving us approximately 619 square meters. Yes, take a pass. And are we good on what's on the screen? Still getting? If you have already taken down what's on the screen, start taking a look at the problem 2 on the back of your notes. That's the one that's on your own, and it is a Centio question. Once again, we have from this screen what we need. Take that as a yes. There's only 12 of you logged in. Please make sure that you're logging in with the Centios. No, you don't. Once you have a formula, you don't need to use the net anymore.
3, 4, 5, guys.
Oh, okay. All right, and waiting for Okay, very small amount of us got the right answer. It's this green one, 268.9. The 638.3 is really stinking close to half of that. 30.45 is the area of the triangle. And let me show you all of the work for this problem. The lateral area is 26 times 8. Gentlemen, the 26 is the perimeter of the triangle. So your lateral area, the first chunk of your formula, is the 208. And then you need to find capital B. That's the area of the triangular base. Remember, a triangle is just 1/2 base times height. The base of that triangle is 7. The height is 8.7. You need to remember that when you're finding the area of a triangle, base and height have to be perpendicular. So you can't just haphazardly pick any side of that triangle to use as the base. You have to use the side of the triangle that's perpendicular to the height of the triangle that's marked. And then you're doubling that and adding it to the lateral area of 208 in order to get, what was the answer I had on the screen before? 268.9 was the correct answer.
I added 26.
Careful. And I'm guessing that we're still getting from this screen what we need.
Can you move the blue thing over to the other
Plus what?
Language.
10 plus 7, gentlemen. Plus 9. Remember, these triangles are congruent, so the measurements on top apply to the figure on bottom. Yes, ma'am. The 208 is the lateral area. Remember, that's perimeter of the base times height. The perimeter of the base is 26. The height of the prism is 8. And it looks like we've gotten from the screen what we need. Yes, ma'am.
Why are we looking for this? I didn't show them
It did. It was just kind of positioned differently. In this figure, it wasn't resting on the base. It was resting on one of its lateral faces.
Yeah, but how would you know if that wasn't the base itself?
Remember what I said earlier. The bases, ladies, the bases are the two congruent parallel faces. Your lateral faces are always rectangles. So in this figure, on the screen, you would notice I have a bunch of rectangles, and then there's two odd men out, the hexagons. Those are the bases. Whereas in this figure, you notice I have the lateral faces are rectangles, and then there's these two other faces that aren't rectangles, triangles. They are the odd men out. They are the bases. Right? Better on this screen now. Okay, as I mentioned earlier, cylinders tend to be a lot easier than prisms because their formulas are a lot more straightforward. A cylinder, because its congruent parallel bases are circles. Circles, I can't spell it. Because its bases are circles, really the only measurements that a cylinder has are the radius of the base and the height of it. As I mentioned earlier, the relationship between prisms and cylinders is very nice and neat in the sense that, remember how we talked about what happens when I cut a prism open, ladies, and fold out its lateral faces? We ended up with one very long rectangle whose base was the perimeter of the base. Consider the same idea with this. I know it's not perfect, but you get the idea. If I were to take this cylinder and cut it open along the sides and unraveled the lateral face of it, what kind of figure would you be looking at? Another rectangle, and this time, Benjamin,
What was the
who cares? The base of this rectangle is what, as far as the cylinder is concerned? It's the what of the circle? Well, your heart's in the right place, but we don't talk about perimeter of the circle, we talk about its circumference. Yes, the remaining shape is a rectangle, and the base is the circumference. Gentlemen, let's stay focused, please. Of the cylinder, and the height is the same as the height of the cylinder. Which means, once again, the lateral area of the cylinder would just be the area of this rectangle, or 2 pi r circumference times height. So lateral area is nice and neat, 2 pi r h. You see what I mean about how much more precise the formulas for circular stuff are. And then, remember, lateral area is just this rectangle part of it. What haven't I found the area of yet? The bases. Well, there's 2 of them, and they're both circles. So the total surface area is 2 pi r h plus 2 pi r squared.
You add pi already, you pi squared.
No, when you add pi plus pi, you get 2 pi. Okay, do we have from this screen what we need?
Thoughts of the week, you know,
Yes, I know. Okay, last problem I'll have time to get to. Let's wrap it up, please. In problem 3, I'm asked for the surface area of the cylinder. Remember, the formula is on your reference sheet. Ladies, gentlemen. 2 pi r h plus 2 pi r squared. We're just taking the values and plugging them in. Again, cylinders are a lot easier to deal with than prisms. This will give me 2 pi times 6 times 15 plus 2 pi times 6 squared. Simplifying this, since the instructions say to leave my answer in terms of pi, I have, I believe, 180 pi plus 72 pi, giving me a final answer of 252 pi square centimeters. Like I said, cylinders are a lot easier than prisms. Their dimensions are much more cut and dry and straightforward. Okay, and I apologize if that's all I have time for, but again, all that was left in the notes was cylinder stuff, which you probably already agree is a lot easier than prism stuff. Turn the Centillos off, please, and return them to the case. That's it, we're done. We dismiss in about 7 minutes.